Hi everyone, this is Maris, and this video is a follow-up demonstration for my deep learning project, Decoding Cancer Types with Microbiome Data. So I'm essentially just going to show you how to run my code. So here I have the unzipped file. Personally, right now my file is just called Maris_final, but when you download this, it should be different. It should have the proper title, but it'll all work the same way. I have all the most important elements here, and we'll start by opening this R markdown file, .rmd. So if you double click this file, and again, you want to do this after you've unzipped all the data and you have it all in the same directory, just so this R markdown and the Jupyter Notebook in the next step can access all the data. So you open up this R markdown here, and you'll see it starts with data pre-processing. It'll go through some steps. Feel free to read through my comments. I really do this similarly to how I would treat microbiome data in my everyday job. So this is pretty industry standard, as they say. And then here I'll save the data frames as CSV files. I have a copy of the unverified read counts, but it's better practice to deal with the verified read counts, and I explained this in my previous video. So I verified the read counts over here, and then I saved them down here. All you have to do is open this file and run all. And it should take maybe a minute to run. It shouldn't take too long. There are a few steps where it'll just take a little bit of time because the data set is quite large. You might notice that I'm not printing off the heads of any of these data sets. I have some statistics, some tables here, but the reason I'm not printing any of the data frame heads is they can be quite large. And so feel free to double click Control Enter if you want to see any of these data frames, but all you really need to do is open this, run it, and then wait until it saved the metadata and the read counts. So what we should end up with here is this cleaned metadata and the rarefied relative abundances. And so once we have these here in our directory, we're going to navigate over to the Jupyter Notebook file. So .ipynb. We're going to double click this. Now I have this open in VS Code. I typically like to use VS Code when I'm working with Jupyter Notebooks. And here you can see I don't have a folder open, so I'm just going to open the folder that contains all of my final information. So again, like I said in the beginning, mine right now is just called Maris_final. So I'm just going to open this folder, and then over here, this is redundant if you use VS Code, but you can just see everything in the directory that comes out here. So again, from here you can also do it. You just double click this file, and when you see this directory, then your script should be able to access everything in here. So this script is going to access the cleaned metadata, and it's going to access the rarefied relative abundances. So you really want to have these two files reachable by this Jupyter Notebook. This has some data pre-processing steps, but I have a note here that most of the pre-processing is performed in R, just because more standard, more natural to me, bit easier to visualize the data at different steps than it is in Python, at least for me. And what's important to note is that I'm running TensorFlow version 2.10.1 and Python version 3.9.18. And if you're running more recent versions, so like, I guess if you're using WSL or not a Windows machine, like a Mac or a Linux machine, then you might have different versions of TensorFlow that can access your GPU. But I had to set it up this way because, unfortunately, if I have a more recent version of TensorFlow, then it can't see my GPU. All you have to do here is click Run All, navigate to the proper kernel. So this TF212 kernel is the one that has TensorFlow installed properly with the GPU on it. I'd really recommend having a GPU available for this, but it shouldn't be too big of a deal if you don't, because with the GPU, the entire thing takes like a minute or two to run. So importing the data, having a nice glance at it, everything looks good here. What we're most concerned with is that this disease type shows up properly, and it does. And you can read through. I have, at least I think, pretty thorough comments throughout my code that kind of show what I'm doing, just, more in a step-by-step format. After importing the data, splitting it into test and train, it goes into a feed-forward neural network model. And so what I have here in this file is the network with 3 hidden layers that didn't have the dropout layers at first. And if you recall from my PowerPoint presentation, you see this is not a great graph. You don't want the validation loss to be skyrocketing while the training loss is just 0. That indicates overfitting. And I have some comments about this in my code just so that if you open this and run it, you can follow along quite easily. This here is, what's running now is my second neural network model, and you can see here, I've added these dropout layers after my dense layers. And so this helps with the overfitting. It'll take a second because we're running it in real time, but here it is. And these are the graphs that you see in my PowerPoint as well. You can see the accuracy curves for training and validation and the loss curves for training and validation match each other better than they did before. But you still see over here, there's some overfitting because validation loss is going up while the training loss is going down with increasing number of epochs. I have an explanation for this too here. Please do note that some numbers may be dependent on the seed. I set the seed in some places, but I did not set it in all places. So the accuracy might come out to be, for example, 86% or 88% instead of 87%. Sometimes it just depends on randomness. It can depend on the seed. Then the autoencoder runs, it gives the test accuracy. There's a brief discussions of it here. We plot the training history. Again, we've seen these in the PowerPoint presentation, brief explanation here. And again, you don't really have to do anything interactive with this other than hit the run all like I've already demonstrated, and this will just run through the entire thing for you. We have the latent space visualization. Here I have this in my PowerPoint as well, but I have a sort of key, a mapping. So I'm classifying 10 different cancer types, Python indexes starting at 0, so it's 0 to 9. And so if you're curious about what exactly each disease type is in these clusters, you can refer back to this mapping here. It shows you the training data, latent space visualization, and the same thing for the test data, little explanation, center log ratio, PCA. Again, this is explained in my PowerPoint video. Not as good clustering, as you can see here. Then I have the code for the data imputation. And for this, I'm really just using helper function. So I just find this function for imputing missing values because I didn't have data that I removed missing values from outside of Python. So what this will do is that it'll downsample to 500 samples from the test data set, which it hasn't seen because it was running on the trained data set and then testing against the validation set. So this test set is different. And essentially what happens here is you take these 500 samples randomly and then you drop 10% of them and then you impute them. So that's what this function is doing here. And then you visualize them here. And this is part of the code. So just running this impute missing values with autoencoder function gives you this representation. And again, this is something else that's going to change with the seed. So if you run it versus if I run it versus if I restart my kernel and run it again, this might look a bit different. But conceptually what I discussed in the PowerPoint. should still hold. This is not the greatest example here. There's not too much clustering. You see a little bit here and here. You see these clustering here, but again, just depends on some random factors. Depends on the downsampling. Yeah. And then here I calculate the reconstruction error, and you can see the average reconstruction error. It tends to be within or just about around 1 standard deviation of the test data, which I consider to be good. And I discussed this a little bit in my other video, in my main video, but if it's within a standard deviation of the test data, I think that means that, you know, like it's pretty acceptable. It's within the range of fluctuation that the data naturally has. So I was pretty pleased with its ability to impute the missing data. So that's really all it is. It's just unzipping and then this data cleaning R file, R markdown, and then just this Jupyter notebook, and all you really have to do is a few clicks, run one, then run the other. Don't run them backwards. Don't run this one before the R markdown. But that's it. You're all set, and then you have all the results that I have. All right. Thanks for listening, guys. I hope this was helpful, and if you have any questions about this, something's not running, you're confused about some part of the code, or you have any suggestions for me, then I'd love to hear from you. Yeah, I'll see you guys later. Appreciate it. Bye.